In part B of problem 2.2, we want to find the expected value of a geometrically distributed random variable n. So find the mean value of n. We just do this in the old-fashioned way. Well, if we just do this in the old-fashioned way, what happens? What happens is we look at the mean of n and we, according to what I wrote earlier here, we set it to be equal to the sum from 1 to infinity of n multiplied by the probability of attaining the value n. And then we substitute the point probabilities into the sum, and the point probabilities are given by p multiplied by 1 minus p to the n. Wow, this looks confusing. And why is it this looks confusing? Well, it's kind of hard to really evaluate this sum, isn't it? Because we have n here and we have n here, and n goes from 1 to infinity. And it's not really a sum that we know that much about. So maybe we should try another approach. So which other approach can we use apart from calculating the mean value using just its straight definition? Well, one thing that can be extremely useful is the alternative definition of mean value in the case that our random variable is a non-negative random variable. So let me just write here. Since n is non-negative, we may use the definition of the mean of n based on the survival function. So since n is non-negative, we may use that the mean of n is given by the sum of the probability that n exceeds little n. I think it's something like that anyways. For little n going from 1 to infinity. And let's just check in the notes, because I have a feeling that this should be greater than equal to. Great, so this is right. And you can find this in one of the sections on expected values in the lecture notes. It's an extremely useful tool, both in the discrete and the continuous case, that we are able to evaluate the expected value by summing up or integrating the survival function. Now, this is only possible if n is non-negative. That's the only cases where we have proved this formula, so keep that in mind. But since n is non-negative, we may use this, and we may also recall that the probability that n is greater than equal to n is given by 1 minus p to the nth. Now, where do we have that from? Well, we have that from A, right? So just recall this, and then we will just continue on here. So the mean of n, when I plug in this value here, is given by the sum for n equals 1 to infinity of 1 minus p to the nth. And then you might ask, well, how do I evaluate that? The way we evaluate this is by using the geometric series rule, where we know that if r is strictly between 0 and 1, then we have that r to the nth for n going from 0 to infinity is equal to 1 over 1 minus r. I think the calculus version also has a constant a multiplied here, and then that constant a goes up here. I'm not sure, but for our case, it's sufficient to use this rule. So remember this, plug it into your formula collection, and have it for the exam as well. It's a good thing to remember. Now, we know this about geometric series, so the question is now, can we use this formula? And we can almost use this formula. Our only problem is our sum starts in 1, and we need it to start in 0 in order to use this formula. So how can we make our sum start in 0? Well, if I write this, then this is false, right? Because here the sum starts in 1 and here it starts in 0. But what is the difference between these two expressions? The difference is this one has an extra term, 1 minus p to the 0, which evaluates to 1. So the thing I can do is outside this sum, I can subtract 1 minus p to the 0th power, because then I have added it and subtracted it. And what I've done here is plus 1 minus 1 is equal to 0. So the net effect of what I've done is just nothing. But that helps because this is the sum of 1 minus p to the nth power for n from 0 to infinity minus 1. And now I can evaluate this sum using, or this series using my geometric series formula, which tells me that I have 1 divided by 1 minus 1 minus p minus 1. And this is equal to 1 divided by p minus 1. And if I put that into one fraction, I can see that that is equal to 1 minus p over p. So this is the mean value of a geometrically distributed random variable n. And this is also what we will then call the expected remaining lifetime of a person. In the case that n is geometrically distributed, of course. Just before we end it, a small note. What we may notice is that typically the chance of survival will be a great deal bigger than the probability of death. So you can think a little bit about how different values of p will affect this thing here. First of all, you can actually see that if there is a 50-50 chance of death / survival, then what happens is that the expected remaining lifetime is just 1 year, which means that if there is an even smaller survival probability, then the expected lifetime is less than 1 year, whereas if the survival probability is greater than the death probability, then the expected remaining lifetime will be greater than 1 year. So that's just a little bit of fun for this part.